In this section of my presentation, I will describe the process that I followed to import the transportation data set into Hadoop and more specifically into Hive external table. You may recall from my paper that I decided to optimize for queries which were based on the input consisting of year and month. That was to improve the performance of queries in group 3. In order to achieve that, the data was partitioned first based on year. And if we drill down into, for example, year 2007, we will see the second level partition that corresponds to the month of the year. And of course, if we look at any specific month, for example, month 9, well, this is actually where the CSV file for this specific year and month is located. Needless to say, this allows Hadoop very efficiently load the data for a specific year and month without scanning through potentially hundreds or thousands of files and records. Furthermore, let's actually take a look inside one of such files. And we will use tail command just to get a small sample of that file. So you will notice that, first of all, there's a very small, there is a very limited number of columns here, and I will get to this in a moment when I describe the import process that I use, which was implemented as a Python script. But furthermore, 17 here is there's a couple of numbers. There is a 17 that is the date of the flight, and 1 is the day of the week. You may be asking yourself a question: where is the year and month? Well, that is the beauty of Hive partitioning, is that this data can be inferred from the tree structure of the directory. So in other words, Hadoop does not need, basically already knows that those fields for this specific data file are being inferred from basically from the directory structure. So this is really sort of all I needed to do in order to be able to query the data. But let me switch now to my Python script, and I will basically outline the high level functions which I needed to implement in order to partition the data and make the data available to Hadoop. So this is a high level function. I call it invoke ETL, and I will very quickly go through this. But the basic idea is very simple. We provide the source. The function takes the source, which is the mounted snapshot of the transportation data set, and basically, and more specifically, the location of the airline on time directory. Then we get all of the zip files, and basically, based on the name of the zip file, we determine its final destination on the HDFS on HDFS. And the function to do this is build hierarchical path, which is given the name of the file. It determines, basically, the name of the file contains the name and the month. So we extract that data from the file, and using that information, build the destination where that file needs to be unzipped. But before we unzip the data into the final destination, we need to trim the CSV file, because only a small subset of the fields actually is required. And the indexes of those fields are defined in this Python list, and the function to strip columns is here. And again, it's a pretty straightforward process. Unfortunately, it requires reading line by line each file, and then basically this is the crux of this function, where we split the data based on the using the column as a comma as a separator, and grabbing the fields which are of an interest to us. And once we collect all the fields for all the rows, we write that as an output to the final destination. And last but not least, the final command is to using the Hadoop put command to copy the data from the local file system, where the import was taking place, into the basically Hive warehouse data directory. And that is really it. There's not really much else to this. Before I finish, I wanted to also show you something that I haven't really touched upon anywhere else in my presentation, and I want to make sure that it is covered. And that is how the data makes its way into the DynamoDB. And you will see from the other portion of my presentation where I describe the queries and them being executed. This is the part which takes the result of those queries and puts them into the Dynamo database. And this is actually done by the feature where Hive has the ability to store its external data into the DynamoDB, and this is accomplished here by this directive. So thank you so much for your attention. That is all I have. In this portion of my demonstration, I will execute queries to get the answers to the questions which were posed in task 1. As I explained in my paper, I'm using Hive SQL, which is a dialect of SQL language, to get the answers to the questions posed in this task. So for example, I will go ahead and copy the SQL statement for group 1, question 1 query, and I pasted this to my terminal. And once I hit enter, what will actually happen is you will see that a corresponding MapReduce job is created and will be executed on the Elastic MapReduce cluster. So obviously, I'm copying and pasting the SQL statements here just for purposes of the demonstration. I actually have automated scripts that execute all of this and insert the output into the DynamoDB. But rather than me showing you sort of the automated process which hides a lot of details, I'm actually showing you probably the most exposing part of this process, so that you can see the queries and you can see the output produced by the MapReduce tasks. Now, most of those queries run very quickly, 60 seconds or so, but to reduce the time that you have to spend examining my task, I will be pausing the recording, but you should be able to see all of the questions, all of the queries, and the outputs produced by the MapReduce tasks. So I'm going to go ahead and pause the video for now. So I'm continuing with question 2 from group 1. Question 3 from group 1. Question 1 from group 2. Now, question 2 from group 2. Question 4 from group 2. Now, question 2 from group 3 is a bit special. I needed to implement a shell script that feeds different parameters for the X, Y, Z, and the date time um, parameters into the SQL statement. So let me show you first the SQL. So as you can see, the SQL statement is parameterized. So basically for each subquery in the 3.2 query, the variables such for the X, Y, Z, and day and month will be fed into the SQL statement by the shell script. The reason that I needed to integrate with the shell script is because unfortunately Hive SQL at the moment does not have the concept of loops, unlike Microsoft Transit SQL or Oracle SQL. So therefore I needed to do some integration between shell and the Hive. So let me show you very quickly the shell. So as you can see, the shell actually has input parameters that are fed into the SQL script. So for example, there are, you can see arrays that represents the X basically the first leg of the origin, Y being the the destination of the first leg, etc., etc., and then of course the date of the first leg, date of the second leg, etc., etc. So all I need to do is really just run the shell script, and this will in turn execute the query with the right set of arguments. The interesting part, you will see how quickly this gets executed, and the reason for that is because the data was partitioned specifically to optimize for this very scenario. As you remember, if you may remember from my paper, I partitioned the table on year and month. Therefore, it is extremely easy for Hadoop to read only the data that is actually needed, because all the queries center around 2008. So only a very small subset of data that actually needed to be read from disk and basically processed as part of the MapReduce. So as you can see, the queries take on average 8 seconds or so. So we'll actually have no choice but let it run, because it will run off the screen very quickly, and I wanted to make sure that you see all of the output produced by this script. One more note on this 3.2 question is one of the subqueries I was not able to produce the result because I was not able to extract the zip file for the December of 2008. I had some problems with unzipping that file, and I know there was some discussions on the forum as well. So I do not have answer for that specific input. So as you can see, for some combinations, there are quite a few options for Tom to take. In some cases, it's really just one option. But nevertheless, you can see that for pretty much all of the destinations, for all of the XYZ, there was an option for Tom to take, and most of them actually have a pretty good on-time performance, historical performance. And that's it. The script completed, and this completes this portion of my presentation.